Okay, so in this video we're going to wrap up talking about the basics of nuclear notation and how that works, and then get into stability and radioactivity. There are calculations in this unit, and we will get to those a little bit later. A lot of the stuff in this unit is conceptual. I've had some people ask me what questions might look like for this unit, and so we've already seen like a couple IB examples where you have to explain things, so you can expect explanation questions and maybe some multiple choice questions. So we might take a look at a little bit of those later. Just to point something out really quickly, so this is showing aluminum 27 in nuclear notation. Remember, the way you would write this and the way you would say this with words is Al is aluminum. And so verbally, you would write aluminum 27 with the 27 representing the mass number of this particular nuclide. Now, I've used the term nuclide before. Nuclide just refers to a specific nucleus. Okay, so for this particular nuclide, I would say it verbally as aluminum 27. Now, 27 is the mass number. And just to clarify something important, on a periodic table, you might see something like this. Okay, this number right here represents the weighted atomic mass of that atom, and the reason it's weighted is well, it's not that important. It's more of a chemistry thing, but just because there's different types of there's different isotopes, I should say, of aluminum, and each isotope of aluminum has a different mass. And because they occur in nature in different proportions, that's why you see that, decimal answer. The number on the periodic table, this one right here, is not the same as the mass number. And it's a little confusing, but the mass number is not the same as the mass of the atom. And so when I say mass number, that's not the same thing as mass. The mass number, in the context I'm using it, in IB physics, refers to the number of nucleons in that particular nucleus. So when I say the mass number of aluminum is 27, I'm not saying it has a mass of 27, I'm saying it has 27 particles inside its nucleus. In particular, aluminum 27 has 13 protons, because remember this bottom number represents the Z, the atomic number, the number of protons, and that would leave 14 neutrons in this particular nuclide of aluminum. So again, don't confuse mass number and mass. This number down here that you've probably seen on a periodic table, you'll never have to worry about that number ever. That's, again, more of a chemistry thing than a physics thing. Okay, so make sure you understand these two things, the mass number and the average, the weighted atomic mass, they're similar numbers, but they don't represent the same thing. And so make sure when you're writing out your answers and you talk about, the mass number, make sure you're saying mass number and not mass, because it's not exactly the same thing. Okay, so just to do some really quick examples before we move on. On this slide, we've got some basic examples. Okay, so we have sodium, and I just happen to know Na is sodium. Sodium 23 is how you would verbalize this. This has a mass number of 23. Of course, remember that's not the same as mass. The bottom left number represents the atomic number, which by definition is the same as the number of protons. Remember, that's what defines an element. If it has 11 protons, it must be sodium, no matter what else is happening. And remember, the mass number represents the number of nucleons in that particular nucleus. Okay, nucleons being either protons or neutrons. So if 23 of the particles inside the nucleus, if of those 23 particles inside the nucleus, 11 are protons, that must mean that the other 12 must be neutrons, because there's only the two types of nucleons. And over here, again, just to do this really simple example, if we know the number of protons is 12, that means the atomic number is 12 because those two are the same thing. And so I would put a 12 down here in the bottom left. And if I have 12 protons and 13 neutrons, these are both nucleons, and so the mass number would be 12 plus 13, which is 25. And so this would be magnesium 25. Okay, so just really simple review stuff related to nuclear notation. Alright, we can do this just really quickly, and again, this is a very basic thing, but it's also very important for you to know. So I don't mind doing a couple really basic examples. Pu is plutonium. It says plutonium right here. The first question it says is, given this is plutonium-239, determine the number of protons in this isotope. Very easy. Bottom left number represents the atomic number, aka the number of protons, so that would be 94 protons. The number of neutrons would be that mass number, 239 minus 94. So you would just do that in the calculator. Now, do keep in mind, we did talk about isotopes in the last video. That would be 145 neutrons. We did talk about isotopes in the last video. Remember, isotopes occur when you have the same number of protons, meaning the same element, but different numbers of neutrons. Okay? And different isotopes can have different physical properties, like we talked about before. Name the element that would exist both verbally and in nuclear notation if 2 neutrons were added to this nucleus. So if we took this nucleus, the plutonium-239, and we added 2 neutrons, it would have the same number of protons, which means it's the same element, but it would have 2 extra neutrons, meaning the mass number would increase by 2, and so that would be 241. So that would be plutonium-241. Now, if we added 2 protons instead of 2 neutrons, that would completely change the element, and I would have to look on a periodic table to know what exactly that is. It would be something, 241.96. If we were to add 2 protons instead of 2 neutrons, I guess I could look it up, but I don't really feel like it right now. But X would represent the chemical symbol for whatever has atomic number 96. I just don't happen to recall off the top of my head. Alright, so, and just to show you one more example, this is actually a past IB question, and so I've had people ask me, what might questions look like. This is a really simple multiple choice question. It says, which of the following gives the correct number of electrons, protons, and neutrons in the neutral atom? It's a little offset, I don't know why. Cu is copper, but you don't need to know that to answer this question. If it's neutral, remember that means it has the same number of protons and electrons. We can tell down here that the atomic number is 29, so 29 protons. That eliminates B as an answer choice. And that 65 represents the number of nucleons, that's the mass number. So 65 minus 29 would equal the number of neutrons, that would be 36. Okay, so we want 36 neutrons, 29 protons, and 29 electrons for it to be neutral. So the answer there would be D. Okay, so really basic question, but that is a past IB question, just to give you an idea of what those questions might look like. And just one more really quickly. Ag is silver, so it says Ag 102, 103, and 104 are all isotopes of the element silver. Which one of these following is this true statement about the nuclei of these isotopes? Remember, nuclei is just the plural of nucleus. Okay. This is another IB question, so it's a multiple choice question. Do they all have the same mass? Well, no, they don't have the same mass. This might surprise you, but silver 104 has a higher mass than silver 102 or 103. Even though mass number is not the same as mass exactly, they are related. And if you have more, generally speaking, if you have more nucleons, you have more mass inside the nucleus. So they definitely don't have the same mass. They definitely don't have the same number of nucleons. 102, 103, and 104 are all different numbers. And they don't have the same number of protons. Now, if they're all silver, by definition, they have the same atomic number and therefore the same number of protons. And so the answer is not going to be C, it is going to be D. Again, very basic question, super easy question, as long as you know what an isotope is. And so when I said definitions are important, you need to understand concepts and you need to understand facts and definitions. This is one of those questions that's very simple as long as you understand what an isotope is. Okay, so there you go. Now we're going to move on and talk a little bit about stability. We will get back to the last model of the atom, the Bohr model, later on. But really quickly, we're going to start to lead into stability, and we'll talk more about different types of radiation in the next video. Now, let's talk about the stability of the atom. Make sure you add this to your notes. I'm just going to read through what it says. Like charges repel and opposite charges attract. Now, basically what that means is if you have two positive charges, let's say positive and positive, they repel. Okay, if you have two charges that are both negative, they also repel. If you have a positive charge and a negative charge, they attract. Okay, if you've ever heard the term opposites attract, that's where that comes from. So here's a question, and it's a rhetorical question. I don't expect you to know the answer. But the question is this. If you have a nucleus, which is roughly 100,000 times smaller than the atom, meaning it's very, very small, very dense, and you have protons inside of there. Okay, remember, protons have a positive charge. Okay, inside this tiny nucleus, if you have protons super, super close together, they are going to repel. Okay, they're going to want to push away from each other. Okay, in other words, the nucleus really wants to blow up. Okay, so the question is, why does that not happen? Why does the nucleus not fly apart? Now, the answer to that question clearly must mean there's some force holding the nucleus together. Now, this outward force, we know where that comes from. That comes from what's called the electrical force. Electric force. Wow, can't spell electric. The electric force, also sometimes called the Coulomb force. You might see that term, just know that's the same thing as the electric force. Okay, we know why the protons repel each other. Okay, we don't know, because we haven't talked about, what is it that holds the nucleus together. And so that's going to lead into talking about nuclear stability and then radioactive decay and half-life. After we talk about half-life, we will get back to the last model of the atom, the Bohr model, and that's really where you'll see the most calculations in this unit. The calculations we'll be doing in this section are very, very basic types of things. Okay, but do make sure you're taking really good notes and asking questions if you need assistance. Okay, so let's answer this question. I'm going to erase what's on this slide. Let's answer this question. Why does the nucleus not fly apart? Okay, you got this outward electrical force, this outward Coulomb force caused by the protons being really compacted together inside that tiny, tiny nucleus. Okay, so what is it that holds them together? So I'm going to clear the screen. Okay, and so the answer to the question that we've discovered over, decades of investigations is there has to be a new type of force that exists that we didn't know about before. And this new type of force, we gave it a name. This is called the strong nuclear force. Now, the reason, this might seem really simple, the reason it's strong is because it has to be strong enough to hold the nucleus together. Because remember, the nucleus, if you didn't have the strong nuclear force, the nucleus wants to blow up. It wants to, expand outward because all those protons don't want to be close together. They want to push apart. And so, it has to be strong to overcome that. Remember that the word nuclear means having to do with the nucleus. And so this is a force that only exists inside of the nucleus. That's probably why you've never heard of it before. Okay, but the strong nuclear force is the name we give to the force that must hold the nucleus together. And if you look at the second bullet point, it says the strong nuclear force holds the nucleus together, generally speaking. Okay, now, in some cases, it doesn't do a perfect job, and that's where you get things like radiation and unstable atoms and stuff. But generally speaking, the strong nuclear force helps to hold the nucleus together. Unlike the electrical force repelling the protons, which only affects particles with charge, the strong nuclear force works for both protons and neutrons, and this is a key fact. Okay, so what I'm saying is you basically have these two forces. You have the electrical force, which only acts on protons, and then you have the strong, I'm just going to write strong, I'm not going to write nuclear just to save space, but strong force, which acts on protons and neutrons. And so what that means is if you take a nucleus and you add more protons, you basically have more positive charge that wants to repel. Okay, that means the force pushing the nucleus out is going to get bigger. If you add more neutrons, okay, neutrons are attracted together because of the strong nuclear force. So if you add more neutrons, you can increase that strong nuclear force without increasing the electric force, because the electric force depends on charge, and the neutrons don't have any charge. Okay, and we'll talk a little bit more about that later. But this is basically one reason why neutrons are useful for the nucleus, because if they didn't exist, then all you have is positive charge that wants to repel. I said this before, the strong nuclear force has the word nuclear in it because it really only holds inside the nucleus. Outside the distance of a nucleus, it basically drops to zero. Okay, so this is a force that only exists in the universe, basically at the inside of a nucleus, for the most part. Okay, so I'm going to clear the screen. You can kind of think of it like this. The strong nuclear force has a very short range, but it's very strong. The analogy is kind of like Velcro, and I wish in the picture that they hadn't put positive and positive, because of course positive and positive, if you take two protons, they also want to repel each other because of that electric force. Okay, but the strong nuclear force is an attractive force that can help hold the nucleus together, because it acts between both protons and neutrons. Okay, so generally speaking, if you add more neutrons, you can increase the strong nuclear force and make the nucleus more stable. Now, that's not an absolute thing by any means. I'm vastly oversimplifying the physics of how this works. Okay, but I'm just trying to explain the bare minimum of what you need to know for the purposes of IB physics. Now, the last couple things we're going to talk about, a lot of this you can read in your textbook, and I would encourage you to do so. We'll go into more detail later about this. It turns out that if you take a look at every force we've ever talked about, and you look at it at the level of atoms, at the smallest possible level, it turns out that there's really only 4 forces in the universe. Okay, there's what you call fundamental forces. Now you might say, well, we talked about more forces than just 4. Like, what about tension? What about, friction? What about the normal force? Well, it turns out most of the forces we've talked about are actually electrical forces coming from the electromagnetic force. Okay, so here are the 4 fundamental forces. You have gravity. We have talked about that before. You have the electromagnetic force. Most of the forces we've talked about fall under that category. That has to do with basically charged particles interacting with each other. Everything from tension in a rope to normal force. When you press on a wall and you can't put your hand through a wall, that's because the electrons in your hand are repelling the electrons in the atoms making up the wall. And again, that goes back to the electromagnetic force. Okay, the strong nuclear force we've talked about. The weak nuclear force we'll talk about a little bit more. But there's only these 4 fundamental forces in the entire universe. And we'll talk more about that in IB physics too. But that's kind of a crazy thing that we can simplify all of the forces we know about into those 4. Your book goes into great detail about explaining the 4 fundamental forces. Not great detail, but more detail than I want to get into. But this is basically a chart showing you the different types of fundamental forces. Obviously, we're talking about nuclear stability right now, so really we only care about these first 2, the strong force or the strong nuclear force and the electromagnetic force. You can see on this chart, positive and positive charge repel, positive and negative charge attract. When we talk about that, we're talking only about the electrical force, okay, the part of the electromagnetic force. This is the force responsible for holding atoms together. Chemical reactions, molecules exist because of this force. If you think like O2, you've got 2 oxygen atoms held together by electrical forces. Okay, so that's a very important force. But inside the nucleus, for the purpose of nuclear stability, we also care about the strong force, like we talked about before, because that's an attractive force that can hold protons and neutrons together. Okay, so we're not going to go into any detail. You don't need to necessarily copy this chart down or anything, or this one right here. But a lot of this information you can find in your textbook. It would be good for you to look over it. But for the most part, you don't need to know all of the details other than to understand, these bottom two these bottom two rows right here. Okay, if you want to know more information about the fundamental forces, I would definitely encourage you to read your textbook. We will talk about those later on in IB Physics 2, but for now, we'll just kind of leave it there. So, just one more thing. We will talk about one more question, and then in the next video we'll talk about what does that mean if it's stable versus unstable. So here's a question. It says, explain in terms of the fundamental forces we have discussed why neutrons are necessary within nuclei to maintain stability. So pause it here and see if you can answer this question. Definitely look back over your notes and the PowerPoint slides if you need to. Try to answer this question in complete sentences. On the next slide, I have a response. I'm not going to say it's the perfect response, but it is a response that I believe answers the question pretty well. Make sure you, when you're doing an explanation question, that you address each part of the question. So explain in terms of the fundamental forces. That means you need to reference the fundamental forces by their correct names. Okay. Then you need to address why neutrons are necessary within nuclei to maintain stability. Okay. So think about what we've talked about before and try to answer that question. Okay. So on the next slide, I'm going to show you the answer that I came up with. Okay, so here's one possible way to answer this question. It says the positively charged protons in a nucleus repel each other due to the Coulomb force. You could also put just electrical force here. Neutrons are needed for stability because they contribute to the attractive strong nuclear force which helps to balance out the repulsive Coulomb force. Now, I'm not going to say this answer is perfect, but it does address the question. We have answered the question in terms of the fundamental forces. So we have mentioned the Coulomb force. We have mentioned the strong nuclear force. Okay, and we did explain why neutrons help maintain stability, because neutrons contribute to the strong nuclear force, which helps to balance out the repulsive Coulomb force. Now again, we could have gone farther in our answer. We could have mentioned that neutrons, because they don't have charge, they don't contribute to that repulsive electrical force. But this is a place to start as far as answering this question goes. So I'm going to stop the video here. In the next video, we'll talk a little bit more about what does it mean if you don't have a stable nucleus, and then we'll get into radioactivity some more. So please let me know if you have any questions. I will see you in the next video.